This is the video for section 5.1 notes, slides 5 and 6. All right, so it says an offshore oil well is located at W, 5 miles from the closest point on shore A. The oil is to be piped from W to B, a point 8 miles down the shore from A by piping it underwater from W to P, and from P to B over land. If the cost of laying pipe underwater is $100,000 per mile and the cost over land is $75,000 per mile, where should P be located to minimize the cost of laying the pipe? All right, so always starts with a good picture. All right, so we've got this offshore oil well located at the point, we'll call it W. All right, now 5 miles from the closest point on shore. So you go straight out from shore, right? So that would be a right angle. That is the point that we call A. The oil is to be piped from W to B. All right, so B is where the oil needs to end up, all right, which is 8 miles down the shore. All right, so 8 miles from A to B. All right. All right. So now we're piping it by piping it underwater from W to P and from P to B over land. So there is some point P that is somewhere in here, right? We're going to pipe from W to P underwater and then from P to B over land. Okay. And so now the question is where should P be located? All right. Now, also it is W is 5 miles offshore, right? And so here is our picture, right? So the question is where should P be located? All right. So what we have to do is we have to give a variable somewhere here to represent the distance from A to P. So let's call that distance X. All right. So P is going to be X miles from A, which means that P is 8 minus X miles from B. All right. And so now there are a couple different scenarios here. X could be 0, right? Meaning P is right on top of A. So then you would pipe from W to A and then A to B. All right. So X could be 0. Now, X could also be what? Well, X could also be 8, meaning you pipe directly from W to B. All right. And so the domain of this function is 0 to 8. And they are inclusive, right? Because you could have X be exactly 0 and you could have X be exactly 8. Okay, now, is it clear that X cannot be less than 0, like negative? Is it clear that like P is not going to be over here? We're going to pipe this way and then that way. Yes. Is it clear you're not going to pipe beyond B and then back, right? Yes. I think that is clear. All right. All right, so now we need to come up with an equation for cost. All right, so now we need to think about, all right, how are we going to end up with cost, right, in an amount of dollars, right? So how are we going to get a cost? Well, cost is going to equal what? Well, the cost per mile, right? So dollars per mile is going to be multiplied by the number of miles to get the cost, right? So our cost equation, right, is going to be the product of the cost per mile and the number of miles. All right, so let's first of all start talking about underwater. It's going to cost $100,000 per mile times the number of miles. All right, so how far underwater do we have to go? Well, that would be the hypotenuse of this right triangle. So that would be the square root of 5 squared plus x squared. So 25 plus x squared. All right, so that would be our cost going underwater. So we have the square root of 25 plus x squared. All right, and then we're adding to that the cost over land, which is 75,000 per mile times the cost over land. Well, that would just be from P to B, so that would be 8 minus X. All right, and so now here is our cost equation that we would like to minimize. All right, now because we have a function that is continuous on a closed interval, I plan to use the critical number test. So I'm going to find the derivative, set it equal to 0, solve, and then I'm going to plug these original values into this original cost equation. All right, so let's take the derivative. So C prime. All right, so I have 100,000 times the derivative of the square root of 25 plus x squared. All right, and so that's going to be what? That's going to be 1/2 times 25 plus x squared to the negative 1/2 times the derivative of 25 plus x squared, which is 2x, all right, plus 75,000 times the derivative of 8 minus x. Well, that would actually just be -1. All right, and so now I have this equation. We're going to set equal to 0. All right, so half of 100,000 times 2x, right? So the 2 and the 1/2 just go away. So I have 100,000 x divided by the square root of 25 plus x squared. And then I really just have minus 75,000. All right, so now we want to solve. So I'm going to add 75,000. All right, so 75,000 equals 100,000 x, missing a 0 there, divided by the square root of 25 plus x squared. All right, so now we're going to multiply by the square root of 25 plus x squared. All right, but now I also have this 75,000 and 100,000. So I could make this a whole lot easier, right? They're both, divisible by 1,000, right? So this could become 175, right? Now, those are both divisible by, well, 25, right? I could divide by 25. And so if I did that, this 100 just becomes 4, and this 75 just becomes 3. So it makes it a whole lot easier if I divide those numbers. So I have 3 times the square root of 25 plus x squared equals 4x, right? Whole lot easier now to deal with this. All right, so now how do I solve? Well, I'm going to square both sides, right? Because I need to get rid of that square root. So I have 9 times 25 plus x squared equals 16 x squared. All right, so now distribute the 9. So 9 times 25 is 225 plus 9x squared equals 16x squared. So now I'm going to subtract 9x squared. So I have 225 equals 16 minus 9 is 7x squared. So divide by 7 and square root. So x equals plus or minus the square root of 225 sevenths. All right, now obviously the negative is out, but x equals the square root of positive 225 sevenths would need to be between 0 and 8. So now we just check that value. So I'm going to calculate the square root of 225 sevenths. All right, so I'm going to get that value 5.669. So obviously that is between 0 and 8. All right, so now I'm going to evaluate the cost of 0, the cost of the square root of 225 sevenths, and then the cost of x being 8. All right, so I'm going to calculate this one first, square root of 225 sevenths. So remember, I'm plugging into the original function. So I'm going to take 100,000 times the square root of 25 plus the answer squared, right? And then plus 75,000 times 8 minus the answer. All right, and I get this calculated value, 930,718.9. So I'm going to write that down, $930,718.9. All right, what about the cost of 0? So now I'm plugging in 0. All right, and so what is the cost of 0? So 100,000 times square root of 25 plus 0 squared plus 75,000 times 8, right? 8 minus 0. All right, so I get that. So that is 1,100,000. So that is obviously more. All right, and then lastly, I evaluate with 8. So I'm just going to hit second answer. Sorry, not second answer, second enter. All right, and then I'm going to plug in 8 for this 0. So 8 there, and then this one would be 8 minus 8, which is actually just 0. All right, and so now I get 943,398. So 943,398, which is obviously more. And so this is the minimum. So how do we answer the question though? Where should P be located? P should be the square root of 225 sevenths miles from point A towards point B. All right. And so you got to make sure you answer the question. All right, let's move on to the next one. How close does the curve y equals root x come to the point 7 halves comma 0? So how close? So in other words, we're saying what is the closest? So let's call this d, okay, for distance. So what is the closest this distance is? All right, so I want to use the distance formula. So we think about distance formula, really just the Pythagorean theorem. All right, and so now we're thinking uh, about setting up this equation. So we want to take the change in y, right? So the change in y would be the square root of x minus 0, right? And the change in x would be x minus 7 halves, right? And so the distance is just going to be the square root of the change in y, so square root of x minus 0 squared, plus the change in x, so x minus 7 halves squared, right? Now, this is what we want to find the minimum of, all right? But it's a little bit easier, right? Let's say that I square both sides. So I get that, and I get the square root of x squared, which is obviously just going to be x. And then I have x minus 7 halves squared. All right, so now I want you to think, if I have D, let's say D represents a graph that looks like this, that has a minimum, not a parabola, but let's just say it has a minimum here, right? Now, what would the graph of D squared look like? Well, D squared, right, would also represent something that has a minimum in the same exact X value. The Y value would be different, right, because it would be the square of the original one. But the key is that they would have their minimum in the same place. So I'm actually going to minimize this D squared function just to make it a little easier. All right. So I'm going to take the derivative of d squared. Now, I'm not taking like the derivative of d squared, like 2d dt or dx or whatever. I'm taking the derivative of just this function. Okay. So the derivative of this function. All right. So first of all, remember this is just x. So the derivative would be 1 plus 2 times x minus 7 halves times the derivative of x minus 7 halves, which is 1. All right. And so I'm going to set this equal to 0. And so I have 1 plus 2x minus 7, or this thing is really just 2x minus 6. All right, so I'm going to add 6 and divide by 2. So x equals 3. All right. And so that means that the minimum must occur at x equals 3 because, all right, what is the domain here? Well, let's think about that for just a second. All right, the domain. Well, what could x be? X could be 0, right? So that is a closed interval, right? Because if x was right here, right? All right, but then how big could x be? Well, x could actually be infinitely large. Now we know that it's not going to be the answer over there, but the key is that it could be any of those values. All right, and so now we do want to use the um, sign analysis of the first derivative. All right. And so what do I have? The first derivative is really just 2x minus 6. Right. And so we have a 0 here. All right. And then a number to the right, like 4. 2 times 4 minus 6 is positive. A number to the left, like 2. 2 times 2 minus 6 is negative. And so the derivative does indeed change from negative to positive, indicating that there is a minimum there. So how close does the curve y equals root x come to this point? Well, 3 isn't the answer. The distance is the answer, all right? And so I want to calculate the distance, which would be the square root of 3, the square root of 3 squared, which is 3 plus 3 minus 7 halves quantity squared. All right, so I have the square root of 3 plus 3 minus 7 halves. That would be negative 1 half squared, right? So I get 3 and 1/4. All right. And so the square root of 3 and a fourth. And 3 and a fourth, that would be 13 fourths. So the square root of 13 fourths would be the distance. All right. That is slide number 6.